So we have reached the last topic on our chapter on shear, and this topic deals with shear center, which is particularly valid for thin walled sections. So until now we have seen in the last topic the shear flow in thin walled sections, and now we will see that what is a shear center and why is it important for thin walled sections. Now to understand the concept of shear center, first let us look at certain sections. For example, if you look at sections where which have two axes of symmetry, and the principal centroidal axis coincides with the axis of symmetry. This is the I section which we had seen for the thin walled section. This is not a thin walled section, this is a solid rectangle that we have over here. But you see, in both of these cases, both this one and this one, it's a doubly symmetric sections, so it is symmetric about the vertical axis, symmetric about the horizontal axis over here. Same for this one over here. Now, so these are the axis of symmetry, and the your centroid is exactly at the center, and it splits the whole beam right into axis of symmetry about the vertical as well as the horizontal axis. Now for these sections, when you are applying a load, right, so if you have these sections, when you're applying a load at the centroid, so exactly at the centroid you're applying a load. Say this beam is fixed at this end over here, is a cantilever beam. When you are applying a load P at the center, you will see that these kinds of beams, both this one and this one, if you have I section also, it bends and there is no twisting, right? So for example, like these beams do not undergo this warping kind of a thing, this twisting, this torsion, internal torsion doesn't occur, and this is also pretty intuitive to understand. But unlike these beams which have two axes of symmetry over here, if I give you a beam which is something like this, right, and this need not be thin walled, this can be any kind of a channel section. This is called a channel section because it looks like this C over here, so it is called a channel. So for this channel section, so this is a channel which is turned upside down over here. Now for this one over here, so it has one axis of symmetry, whereas if you turn this one over here, it is symmetric about this axis, right? So it is also has one axis of symmetry about here, but about this particular axis, about the vertical axis, it is not a symmetric section, because if you see about the vertical axis, on the left hand side you have this part, and on the right side you have this part, so it is not a doubly symmetric section as you have. Now for these beams, if you apply the load for about the centroid, so let's take a look at for this one over here, for this section. Now if for this section, if you apply a vertical load passing through the centroid, you will again have the case where there is only bending and no torsion. So let's take a look. So if you have something like this, the line of action of P, it's a cantilever beam. If you put a load through here, you see this has already bent, so it has only bending, but there is no twisting or no torsion. On the other hand, on the contrary, for this one, and this is also takes a bit of your imagination, and you can maybe do this experiment at home as well, like these channel sections. You may not have a steel channel section, but the electrical wires in your house which passes through the through the wall, and to conceal them you put these these kind of channel sections that you have made of plastic, right? So if you happen to have some at your home, you can try it out, that if you keep the beam like this and if you apply the load, can you sort of intuitively imagine what is going to happen? It is going to bend for sure, but it is also going to have some amount of twisting, some amount of torsion. So let's take a look. So if you have something like this where the load is again acting through the centroid, and you can intuitively imagine that along with bending, it is going to have some amount of twisting as well, right? So this is an experiment which is done on the lab, and that's why I've written based on true story. So you see here, this channel section that you have, it was fixed at the one end over here, and this load, this line of action of the load, it passes through the centroid. So this C over here, if you see, the originally the line of action passes through the centroid. Now when this guy has bent, along with the bending, it has had certain amount of twisting also. You will do this experiment in your solid mechanics lab as well. There you can see that this kind of phenomena exists. It is valid. Now the question is that why does it happen? Why, when for sections which have only one principal axis of symmetry and not the other axis of symmetry, when we apply the load over here, why along with bending do we also have torsion? So let's go ahead and take a look. And why is it important? Because if this section is thin walled, right, it undergoes significant amount of torsion, and thin walled sections are essentially very weak in torsion. That's why we need to take into account or learn about this concept of shear center when we talk about thin walled sections which have only one axis of symmetry. Now let's see why it happens. Now this is again the similar kind of a beam over here which I have taken, where the load is applied through the centroid. Now if you take an internal section, right, if you take that internal section over here, this is the resisting force that you are having. This resisting force equals to P, and then because of the shear flow, remember we have considered the shear flow over here. Because of the shear flow, you are going to have these horizontal loads which are acting on the top flange and the bottom flange over here. Remember, here again the top is the flange, the bottom is the flange, and the middle portion is the web over here. Now I hope you are clear with this direction of the forces. This is essentially like if you are say taking a beam. Let me turn on my pen so that I can show you. So suppose if you are taking a cantilever beam for that matter, right, what you have over here, and if you're applying the load, say a load P which is acting, if you take a section somewhere and you're only taking the right hand half, only this part over here, what you essentially see is that you have this load P, right, and you will have this V and the moment and so on. So I'm not drawing the moment. So this is the V equals to P that you are having, which is essentially this guy, this vertically acting load over here. So you're looking at an internal section over here, right? Now along with this, you will, because of the shear flow, remember that we had seen for the thin walled eye sections that it is like the flow of water. So here at this interface, you are having this vertically acting V over here. So according to the direction of the flow of water, the water must come through here, it must go through up, and it must exit over here. So you are going to have some amount of shear flow is over here in the horizontal planes over here. Okay, now if we take a look at this one, just this small section that we are looking at, if we take a look at this one, this is how the flow of shear happens. Now remember, here again your vertical acting upwards force in this section, if you look at the section overall, if you look at a complete zoomed out view, you have this vertically acting force V, which is equals to P in this particular case, and that gives rise to this shear flow over here. Now this is again like the flow of water, you are having a vertically upwards acting force, so that leads to the flow of water. It must start from here and it is 0 over here. Remember at the edges, remember what we had discussed, that at this edge over here as well as this edge, the magnitude of the shear flow or the shear stress tau, right, because they are correlated, must be equals to 0, because on the plane which is going into this slide over here, you do not have any externally acting shear, so the complementary shear must also be 0, whereas internally you must have a substantial amount of shear flow or the shear stress over here. Also remember, since it's the flow of water, this vertical arrow that you see over here must be equals to this arrow over here. Now last thing to remember from what we had seen before, that if the line of action of the force, this V, is acting vertically up over here, for what we had learned from our previous discussion on shear flow, is that for sections of the member which are perpendicular to the line of action of the force, this the shear flow is also perpendicular, it acts parallel to the edges, and in the in this vertical section, which is parallel to the line of action of the force, the shear flow is going to be parallel, right? So if we now draw the magnitudes as we had done in the previous example, you are going to have a linear variation. Remember, in the horizontal members, that is the members which are perpendicular to the line of action of the shear, the flow, the nature of the shear flow or the shear stress is linearly varying. So it is going to vary from 0 over here to a maximum value over here. Then in this section, the variation is going to be parabolic, and then again it is going to be linear. So it is look something like this over here, and you can easily derive this one. For example, how will we get this tau f over here? We take a small section, we have done this already. We'll take a small section, you find the q of that section, from the q you can get the tau. Now remember that this, what you're looking at, is a shear stress, or if you the diagram for the q is also going to be the same. It is just will be this tau f times the t, the thickness, which we have looked at, right? So here this is the shear stress. So now from the stress, if I try to get the force, how do I get the force from the stress? So here the force from the stress would be simply, so this is the triangular. So remember, we always try to idealize, and remember one more important thing, these triangles and this parabolic part, it is only a representation of the magnitude, not the direction. The direction of the shear flow, the shear stress happens something like this over here. Now from the tau f, now from this stress diagram, if I try to get the force diagram, so this is how it looks like over here. Now a quick question, how do I get this ff over here? It is simple. This ff you can simply get, see the stress varies from 0 over here to maybe a highest magnitude something over here. So it is going to be, you know, half times the length of this one times the height of this one. So that will, you know, give you the dimension of, you know, the length 2 times if you multiply, you know, the value of the peak stress over here, you will get this ff. We'll do a problem example there. You can see that how we get this from the shear stress distribution. How can you get the forces? So anyway, the in a nutshell, what I'm trying to say is that here, because of this, you know, tau f, you are getting a total. So this is the total force, because the force is just, you know, one quantity. It is not, you know, varying from small to large. This is the total resultant force which is acting on, you know, this horizontal face. And as you can say that this ff and this ff is going to be the same, because, you know, about this horizontal axis is symmetric, so it is going to be ff and ff is going to be same. And this one must be equal to P, because externally you are applying P. So to obtain the vertical force equilibrium, see, these horizontal forces are automatically balanced, because, you know, this is equal in magnitude and opposite in direction to this one, so that is balanced, and this P must be equals to this externally applied P over here. Now very important, now you have to closely observe over here. See here, these two are equal and opposite forces which are separated by a distance h over here. And also, if you look at, you know, this structure, if you look at this entire section, the section which you've cut over here, essentially from here to here, if you look at this entire section, the line of action of the P at this end is at the center. So if I have to, you know, sort of quickly mark that, so this is my line of action of the externally applied P which is acting on that section. Now because of that P itself, internally you're having that V which is equals to P over here. Now take a look at these forces. This ff and this ff are equal and opposite forces separated by a distance h. Similarly, this P and this P are equal and opposite forces separated by some distance wherever the centroid is. Now can you now understand that why along with bending you're also having a certain amount of twisting? Yes, you're right. You see this ff and this ff over here, this force and this force forms a couple, you know, positive couple. So it forms, you know, a couple like this over here, right? Similarly, this force and this force equal and opposite separated by a distance, that also forms a couple over here, right? So as a result of this overall couple, you are getting that amount of twisting that you are having. So if we just go back to the previous slide, right, so this is the twisting because of these internal forces developing at the section. See, this is also twisting in a clockwise manner, exactly what we saw over here, exactly what we saw. This kind of twisting happens in a clockwise manner. That's why you have a twisting kind of a phenomenon. Now, so the question here is that how do we, you know, sort of resist, you know, this you know, twisting kind of a motion that is there? How do we resist this, you know, twisting? So as a result of this twisting, we saw that you're having, you know, the twisting in the beam over here. Now you see what is there in our hand. What is there in our hand in terms of this beam? We cannot do anything with the beam. The beam is as it is. In our hand is where we can apply this force P so that it cancels out this twisting moment that you're having, and essentially does not let the beam, along with bending, does not let it twist. Now if you see, this ff and ff times h causes a moment which is ff times h over here, right? So let's just quickly write that. So this guy over here, sorry, I should turn my pen on again. Yeah, so this guy over here and this guy over here, separated by this h, causes this particular moment. This is ff times h, right? So this is the moment, this guy over here, the moment that is happening, it is f times h, right? So this is the twisting moment over here. Now to cancel that moment, instead of applying P at the centroid, so to cancel this clockwise moment, I must have an anti-clockwise moment somewhere. I must sort of put my load P at a particular place where it causes an anti-clockwise moment equal in magnitude to this ff times h, so that the entire twisting moment is cancelled out. Now I am free to apply this load P anywhere about this horizontal axis. Here I have applied at the centroid. I can shift it to the right, I can shift it to the left, I can have some attachments to the beam, and I will come to the picture for that one. I can have some kind of attachments or some kind of configuration where I make the line of action of P, and as you can imagine, this P, instead of applying to the center, if I apply over here, so suppose if I'm applying the P over here, see this, if I apply a P here, so let me maybe hypothetically draw it. Suppose if I'm applying this P over here, right? This P, and see this P is always going to be there to balance out the externally applied load that is there. So if this P and this applied P over here causes an anti-clockwise moment, which can help in resisting this clockwise moment over there. So let's go ahead and take a look. So the question is that, can there be a location of P where as a result of applying that load P over there is not going to be any amount of twisting? And yes, the answer is true for that. So if for this one, if I apply a load P in that external beam over there, which is at a distance to the left of the section, where this P and this internal P over here, I can have a total moment. So I can have a P times E, which is the anti-clockwise moment. See, this is also the internal P that is developing over here. So let me just write that here as well. See, if I have this equal and opposite P separated by a E anti-clockwise moment, this should be sufficient to resist this clockwise moment. So if I just do this P times E and I choose the E, the distance E over here, such that equals to ff times h, then I'm completely nullifying the clockwise moment due to the ff times h over there, and I can resist the twisting of the beam. So this is the concept of shear center. So now so what is the shear center? Shear center is essentially this distance E. So shear center is the distance at which you should apply the load P such that the beam only bends and it does not twist. So force P applied at a distance E helps cancel the twisting moment over here, and this, my friends, is known as the shear center. So this particular distance that you see over here, this tells you where this particular point is, or where the shear center is, right? So let's take a look. So shear center is the point where the application of the load will not cause any twisting but just bending over here, right? So if you take a look, it is somewhat like this over here. You see, now instead of applying the load P at the center, I have somehow shifted it, right? Now how is it practically possible to do? So now see, in this example which I just showed you, previously the load was acting at the centroid. Now I have shifted the line of action of the load to the left of this channel section at a certain distance. So you see, this one is just now bending. It does not have any amount of twist. So let's compare it with the previous figure that we saw. See here, when the load was acting at the centroid, you were having bending and some kind of twisting over here, clockwise twisting. Now what I have done is that I have applied the load at a certain distance P to the left, such that you are having only bending and no amount of twisting over here. So this E gives you, this is exactly the formulation that we wrote over here, that is P times E. So this is again the P, the internal shear that is developing, that is V equals to P. So P times E is FF times A. So E gives you the location of the shear center in this particular case. So I hope this overall concept was clear. So what we are going to do is that we are now going to look at a problem example where we are going to take a similar channel section, a similar kind of a section like this over here, and for that we are going to compute the location of the shear center that is there. So let's go ahead and take a look at a problem example.